Hi, and welcome to the Build Your Own Data Logger course, brought to you by FreakLabs and WildLabs. I'm Jacinta from FreakLabs. This is Module 3, Submodule 6, Interrupts. So we've nearly finished programming our basic functionality. Congratulations for making it this far. In this final submodule, we'll be tackling an advanced programming concept, and one that even experienced embedded programmers get nervous about using: interrupts. Interrupts, as the name suggests, interrupt our application code. The reason they're a little dangerous is because we don't control exactly when the interruption will occur and what our application code will be doing when it's interrupted. This can make our application, and therefore our device, unpredictable. And in programming, we don't like unpredictability. So why use interrupts at all? Well, because they're really useful, and they're a key part of our low-power strategy. But first, let's explore a programming world without interrupts. That is, a world of sequential programming. Sequential programming is when an instruction or piece of code is executed in a series of steps that are in a specific order that we have specified. By that we mean an instruction is only executed after the previous instruction has been completed. As programmers, we specify the instructions and the order in which they execute, so we have a lot of control over the program. In this wonderful world of sequential programming, our embedded application, and in fact a lot of technology in general, would be more predictable and stable. Sequential programming is how our code on the WildLogger is structured so far. When our WildLogger is powered on, or there's a system reset, the WildLogger executes the setup function first, then goes into the loop function, and essentially lives there for the rest of its life, happily executing the same instructions according to the logic that we've created. Sequential programming is great, and means that once our application is coded, loaded, and tested, our work is done, and we can spend the rest of the time in the mountains singing, "High on a hill was a lonely goat herd, lay, hoodle-lay, hoodle-lay, hoo-hoo." Not so fast. That's just not how the world works. We and the devices we'll build and deploy, like our data logger, operate in a world full of interruptions, or what we call in programming, asynchronous events. In the real world, we and our devices have to respond to these asynchronous events before we can get back to whatever it was we were doing before. This is called asynchronous or event-based programming, i.e. when an event independent of the main program flow occurs and we handle or respond to it within the program. Let's look at life, or maybe just my life, as an analogy. At the start of the day, I have a to-do list, which I start going through in the order that's on my schedule. Once one task is finished, I'll move on to the second task, and then on to the third, and so on. This is sequential programming. However, because it's a messy world, despite my best efforts, I'll be interrupted. It could be someone walking into the room and asking a question. It could be an urgent message on a chat program, because they are always urgent. Or it could be me constantly checking my email for a field trip confirmation. Although sometimes I deliberately go offline or I hide in the field just so I can be alone and uninterrupted. Anyways, in each case, I'll need to handle the interruption before I can get back to what I was doing. Sometimes I'll even need to completely switch the tasks I do for the rest of the day based on the interruption. This is event-based or asynchronous programming. You might be thinking, but hang on, waiting for a field trip confirmation via email, that's not really an interruption. We're waiting for the email. And you're right. We're waiting for this asynchronous event. We don't know when it's going to occur, but we do want it to happen. In this case, what would be more efficient for our productivity is to be notified when the event occurs, rather than constantly checking our email. The notification could be a sound, a bell, or even flashing lights and sirens. Once we've received the notification, we interrupt whatever we're doing, check our email, and then either go back to what we were doing or reply with a "Woohoo! We're going into the field." Let's bring it back to our data logger. Let's imagine we want our data logger to take a sensor reading whenever an animal walks past. In event-based programming, an event occurs, i.e. the PIR motion sensor detects the animal has walked past. The microcontroller gets triggered, stops whatever the device is doing at that moment, and jumps to a special function that handles the event and then processes the response. You may be thinking, why don't we just constantly check the main loop function for the motion detection and then respond to it? Why do we have to stop everything? Well, we could do this. And when the main loop function constantly checks for some kind of event and then responds to it, it's called polling. In fact, we're already doing this with our command.poll function when we're constantly checking the serial monitor to see if any keywords have been typed in and then responding by calling the associated function. Polling is a reliable and predictable, meaning safe, way to deal with events, and there are many programs that use this method. And if we're not worried about power consumption, it's a perfectly valid way of checking if an event has occurred. However, because our devices are going in the field and we want them to last as long as possible on batteries, we do care about power consumption. Part of our power saving strategy is to put our device to sleep or in low power mode whilst we're waiting for an event to occur, such as the motion sensor to be triggered. And one problem with polling is that you can't do it whilst the microcontroller is in low power mode. In fact, there are only two ways for the microcontroller to come out of sleep or low power mode, either through a reset or, you guessed it, an interrupt event. This strategy to sleep and wake up via an interrupt is central to many devices. On a television, for example, when you push the power button on the remote control, you're not really turning the power to the device on or off. You're actually signaling to the television to go into or come out of low power mode. When it's off, the television still retains some power since it needs to monitor the remote control to see if there's an interrupt event to wake it up. So when you push the power button on the remote control receiver gets the event, issues the interrupt to the sleeping system to wake it up and power everything back up. For a field device like a camera trap, it's the same thing. What you want it to do is to sleep all the time, and as soon as an event occurs, trigger an interrupt to wake up the system. You can then check the source of the interrupt was the PIR motion sensor and start taking video footage or a still image. Once it's finished and written to the SD card, you put the system back into sleep mode and wait for the next event to occur. So, okay, we get the idea, but how does it actually work? There's a special pin on the microcontroller called an interrupt pin, which is sensitive to what's called transitions. A transition is simply when a pin changes from high to low or low to high. When the interrupt pin transitions, the microcontroller sends a signal to stop everything that the device is currently doing and to jump immediately to a special function that we've defined. That special function is called an interrupt service routine, or ISR. Inside the ISR, we give instructions on what to do or how to handle the event. So we need to both initialize our interrupt pin and map a function to it. On the WildLogger board, the interrupt pin numbers are 2, 3, and 6. Don't worry about the interrupt number just yet. We'll get into that into the next video. Inside our interrupt service routine, we're going to do the bare minimum, which is to set a flag and then immediately jump out of the routine or the function. The longer we stay in an ISR, the higher the chance that we'll introduce nasty bugs into our program that are notoriously difficult to find and then debug. So interrupts are actually quite a complex topic in embedded software development, and they're the principal engine behind operating systems and how they're designed. In our data logger, we're only going to use interrupts mainly just for power management, where we'll be waking up the device. So in our ISR routine, we're going to be setting a flag, then jumping straight out of it and letting another function handle the rest of the interrupt response. So in this lab, we got introduced to the concepts of interrupts and how we'll be using them. We'll be using them in the simplest way and mainly for power savings. But before we get into using them in power management, we'll be using them with the push button, which is also very useful. So in the next lab, we'll be learning how push buttons work, how they operate as an interrupt, writing our first ISR, and writing our first function to handle our interrupt event. See you in the next module, Lab 6A, Push Buttons and Interrupts.
High on a hill was a lonely girl.